So in the last class, welcome to the series of lectures on Higgs mechanism. In the last class, we have discussed the potential energy and kinetic energy for the fields and derived Lagrangians for a scalar field. So in the last, we have found that the potential energy density can be written as square of the field, and the kinetic energy will be direction of the field with respect to space and time. And from this we have obtained the Lagrangian, that is half of del mu phi, where del mu phi means del phi by del x. So this one and then this one minus the potential energy, kinetic energy minus potential energy, which I have taken mc square by h cross phi square. This is the potential. In the particle case, we take half mv square. This is the mass portion. So, or we can write it as phi minus half mu square phi square, where mu square is this portion, which includes mass. Okay, so this was our Lagrangian, and we obtained equation of motion. We have the equation of motion for that is del mu del phi by del x mu minus. This is our Euler's Lagrange equation for fields. If you substitute here, first differentiate this one with respect to dl, or you substitute del phi. First work out this one. This will give you minus mu square phi. Then this one, delta L by delta mu phi. So this will give you it is giving del mu phi. Take it as now del now this one is the derivative of this. So it means derivative of this. It means del mu square phi. So if you substitute here in this equation of motion, you will get del mu square phi minus, or it's minus what it is, plus mu square phi. So this is our equation of motion. This is just like our can write it. This is just like our equation of motion for particle, simple Hard motion for particle, where d square x by dt square plus omega square vector. This is just similar to this. Here instead of position x, we have the field. Now this position varies with time. Here the field varies with both space and time. Nu has 4 components, 1 component for time and 3 components for space. And here this is the mass term, omega terms, and this is instead of x we have time. So you can say that this is just like this is a simple harmonic motion for the field. Now, the potential energy part of the field, which we have written here as the potential energy part. Potential energy density was half mu square phi square. And it means the potential energy, just like in the particle case, the potential energy is half mv square, or now it's half kx square. Half spring case, in case of spring we have found that the potential energy was half kx square, k is the spring constant. It means the potential energy in that spring varies as the square of the position. Here also the potential energy for the field varies as the square of the field values. So the graph of the variation of the potential with the values of field will so the variation of the potential with field the variation of the potential energy with phi will depend, if nu is taken as positive, nu is positive, this is the our you can say it's a mass term also, and m c square by h, or if this value is positive, this parameter is positive, then the potential energy varies as a parabolic, follows parabolic path. Potential energy phi is here 0, it varies from plus minus values, and for then we have taken nu square as positive, then the variation of the potential energy with the field will be parabolic like this. Now if you take so we have, okay, I'm writing here the Lagrangian. Our whole Lagrangian was half del mu phi minus half mu square phi square. So if this was positive, we have the graph proportionality curve like this. Now if you take mu square as 0, the parameter mu square as 0, it means we have no proportionality. And if for mu square as 0, this parameter 0, it means we have no proportionality part and we have only field varies with space and time, which is given as a kinetic energy, but without the potential energy, means this has the corresponding mass of the field is 0. That is, the quanta of the field is 0, that is massless. The field quanta due to the variation of the field is 0, that is massless particle. This has no rest mass. Although it possesses kinetic energy, but it has no mass, it's massless particle. Now if you suppose mu square as negative, in that case the potential energy will be inverted. The parabola will be inverted. So if we take mu square as negative, about the variation of the potential energy with the field value will be like this. Field value, and this is the potential energy. That is, parabola is upside down. This is like a particle on the top. That particle cannot stay here. For the potential, the field is now unstable. In case of mu square as negative, the field is unstable. Any particle, quanta particle, cannot stay at the top. It just fall down. So this is the three cases where we has taken mu, the parameter mu as different values, mu as positive, 0 and negative. Now we will do something about Maxwell's equation we have, and I am drifting from the we are discussing today Maxwell's field equations. If you will require that, that's why I am doing Maxwell's. Just we know that Maxwell's field equation we all know that the Maxwell's field equations, four Maxwell's equations, called of H. Current density plus 1 by C, and the curl of E minus 1 by C dV by dt, where d is epsilon times and E is mu times. So these are the four Maxwell's equations which we all know. Now this divergence of B is 0 can be written as, if divergence of B is 0, then B can be written as curl of A, where A is electromagnetic field. Because this is a vector. If you take the divergence of B will get 0, because divergence of curl of this vector field is 0. So B can then be written as curl of vector field, say A. Now if you take this one here, this equation, and substitute the values of B, curl of B, you will get curl of E minus 1 by C dV by, but the B is given by curl of A, so it will be minus 1 by C dV by dt, curl of now if you bring it in the same side, curl of E, this becomes 1 by plus 1 by C d by dt of curl of. So this is again a vector, curl of this vector. This vector can be written as a gradient of some field, scalar field. So we can write this E plus 1 by C dA by dt as gradient of some scalar field, say phi. That's from this we get E is equal to minus del phi minus 1 by C dA by. Now the electric field is represented in terms of scalar field and a vector field, and the magnetic field is also represented as a vector field, called a vector field. So this electric field and magnetic field are represented in terms of a scalar field phi and a vector field A. Okay. Now these electric field and magnetic field, which are represented in terms of scalar and vector potential, this can be done in a tensor form. So we can write electric field E and magnetic field B in terms of magnetic field E and magnetic field B can be represented in tensor form. Denoted as F mu mu. Now F mu mu F mu is delta A mu by delta x mu minus delta A mu by delta x mu. This is F. Where mu and mu are indices, have values from 0, 1. 0 corresponds to time component and this x, y component respectively. If you write, suppose take mu as 1 and mu as 0. Mu as 0 and mu as 1. Suppose we have taken that mu as 0 and mu as 1. Then it will be the first f 0, 1. That is delta A 1 by delta x 0 minus delta A 0 delta x. Here A0 corresponds to scalar field and rest A1, A2, A3 will correspond to x component, y component, z component. This is the scalar. So here this means delta Ax by, this is C delta t, the time part, minus delta A0, delta phi. So it is delta Ax by delta t, delta Ax by delta t, C, and this is, oh sorry, this A1 is minus. So it is, this gives you Aex, this is delta phi by delta x and minus 1 by c delta A. Similarly, if you take, suppose mu as 0 and mu as 2, let us take mu as 0 and mu as 2. It means F02, F02. This is delta 2 by delta x naught minus delta A by delta x. This A delta A2 means minus delta AY by C delta t minus delta A naught is delta phi by delta y. So this you will get EY. That's EY means delta AY by delta t minus delta phi by delta y. So this gives you now suppose one more example. Take mu as 3 and mu as 2. You get 3, 2. Delta A2 by delta x3 minus delta A3 by delta x2. Delta A2 means delta AY, and this is delta Z. X3 means Z component minus delta AZ. dz by delta. So it is x component. If you take the curl of vector A and its x component will give you. So in this way we can obtain all the values of f, the tensor, and the values of the tensor will be like this. Okay, I wrote this one. Yes. So we will get f mu as f00 is f10 was x. This is 0 E1, this one, and then you will get Ez minus Ex minus Ey minus Ez 0 minus Ez dy. dz 0 minus dx minus dy. So you get the whole tensor like this, and we have just written that where f mu was delta a mu by delta x mu minus delta a mu by delta x mu. So this is our whole representation of this. The representation of this is this tensor. So the Lagrangian for electromagnetic Maxwell's field equation. The Lagrangian density for this field equation will be equal to half of 1 by 4 pi f mu f mu plus j by c j mu. The j is the current density. Zeroth component means charge density, and just is current density. However, we have 1 by 4 pi f mu means delta a mu by delta a mu by delta x mu minus delta a mu by delta x mu, and this delta a mu by delta x mu minus delta a mu by delta x mu plus j mu by c. So this is our Lagrangian. The first part, this is the variation of the field with space and time. This is the variation of the field with space and time. The A is the field, it constitutes both the vector and scalar field with variation with respect to space and time. So this portion is the kinetic energy part, variation of the field with space and time. And this is the potential energy part. Okay. Now we want to write the equation of motion, and we have the equation of motion for the, which is called as Euler-Lagrange equation of motion, means delta mu means delta L by take this one only. Oh. Mm. Sorry. Yes, that's it. Oh, no, here, sorry. Me here and so first of all, work out this one, variation of the Lagrange with respect to this value. It is you will take the variation of, differentiate this one, you will get 1 by 4 pi. This one will be differentiated, this will be 0, minus 1, and this remains as it is. Now if you again differentiate this one, because we did differentiating with respect to del x, del by del x mu. So we get okay, yeah, or you can simply write like this, 1 by 4 pi del a mu by del x mu minus del a mu by del x. So this one. Now this portion, delta variation of a L with respect to del a mu, this will be differentiated. So it will be delta L by delta a mu will give you j mu by c. Now just substitute the value of this we have obtained, the value of this we have obtained. Substitute here this is Euler's Lagrange equation. So if you substitute the values of in this Euler's Lagrange equation of motion, we will get the variation of here, this will be delta by delta x mu, delta by delta x mu, and this part, the variation, this is minus 1 by 4 pi delta a mu by delta x minus delta a mu by delta x mu, and then we have a term minus, because minus sign here, differentiation of this gives you j mu by c is equal to 0. This is f mu nu. So we can write it like this in the compact form, del by del x mu of f mu. Take this as, so it is 4 pi by c j. So this is our Maxwell's equation. Where f mu is given by this formula. So we are mostly interested in this f mu or f mu. This is delta a mu by delta x mu minus the magnetic field tensor. So in the future we have to use this one, delta a mu by delta x. This gives you the electromagnetic field tensor and give you the whole values of electric field and magnetic field significant from this values. So this is up to, just to remind you, just to recall our Maxwell's field equations, because we require this Maxwell's field equation in our next classes. That's why this is just to recall the whole Maxwell's equations. Okay. Thank you.